Welcome to this coding tutorial. In this session, we'll be tackling the problem number 441, arranging coins. We'll break down the problem, explore possible approaches, and guide you step by step to the solution. Let's dive in and start solving. In this problem, you are given a total of n coins, and the goal is to arrange these coins to form a staircase. Each row in the staircase must contain a specific number of coins, or the ith row has exactly I coins. For example, the first row will require 1 coin, the second row will require 2 coins, and so on. The important condition here is that you must fill each row completely before moving on to the next one. Based on the total number of coins provided, your task is to determine how many complete rows can be formed in the staircase. The input is an integer n, which represents the total number of coins, and the output is another integer that represents the total number of fully completed rows. The constraints for this problem specify that n will always be a positive integer, ranging from 1 to 2 to the power of 31, which means the solution must be efficient even for very large values of n. To better understand the problem, let's look at a couple of examples. In the first example, if you have n equals 5 coins, you can build 2 complete rows. The first row uses 1 coin, the second row uses 2 coins, but when you try to build the third row, you only have 2 coins left, which is not enough to complete that row. So, the total number of complete rows you can form is 2. In the second example, if n equals 8, you can form 3 complete rows. The first row takes 1 coin, the second row takes 2 coins, and the third row takes 3 coins. After that, you only have 2 coins remaining, which is not enough to form the fourth row. Therefore, the total number of complete rows is 3. These examples illustrate how the problem is solved by sequentially filling each row until you run out of coins. Now consider another example where n equals 1. Here, you only have 1 coin, which is just enough to form the first row, but no coins are left for any additional rows. As a result, the total number of complete rows is 1. Let's also review the constraints and edge cases for this problem. The input n will always be at least 1 and can go up to 2 to the power of 31, which is the maximum value for a 32-bit integer. This means our solution needs to handle very large numbers efficiently. Some edge cases to consider include the smallest input, n equals 1, where only 1 row can be completed, and a case like n equals 6, where you can form 3 complete rows with 1 coin left over. Finally, for the largest input, n equals 2 to the power of 31, the solution must still work correctly and efficiently, even with such a huge number of coins. To solve the problem of arranging coins into a staircase shape, we can start with the simplest approach, the brute force method. The intuition behind this approach is to simulate the process row by row. Starting with a total of n coins, we attempt to complete each row by subtracting the required number of coins for that row. For example, the first row needs 1 coin, the second row needs 2 coins, and so on. We continue this process until we run out of coins to complete the next row. The algorithm is straightforward: initialize a variable row to 0, and as long as you have enough coins to complete the next row, increment row and subtract the required number of coins from n. Finally, the value of row at the end gives the total number of fully completed rows. While this method is easy to understand and implement, its time complexity is k, where k is the number of rows that can be completed, which grows roughly as the square root of n. This means that for very large values of n, the approach can become inefficient. Additionally, it has a space complexity of 1, as no extra memory is required. The trade-off here is that while the brute force approach is simple, it can be slow for larger inputs due to the iterative subtraction process. A more efficient way to solve this problem is the mathematical approach. The key insight here is that the total number of coins needed to form k complete rows is given by the sum of the first k natural numbers, which can be represented by the formula k plus 1, / 2. To find the largest k that satisfies this condition with a given n, we can rewrite the inequality k plus 1, / 2 equals n as a quadratic equation, k2 plus k, 2n equals 0. Solving this using the quadratic formula gives us k equals -1 plus sqrt, 1 plus 8n, / 2. The result of this formula gives us the maximum number of complete rows that can be formed, and we take the floor of this value to ensure we only consider whole rows. The algorithm is remarkably simple. compute the value of k using the formula and return its integer part. This approach avoids iterative calculations entirely, making it much faster and more efficient, especially for larger values of n. The mathematical approach stands out for its efficiency, with a time complexity of 1. This is because the computation involves only a fixed number of operations, regardless of the size of n. Similarly, its space complexity is also 1, as no additional memory is required. The main advantage of this method is its speed, making it an excellent choice for very large inputs. However, it does require careful handling of floating point calculations to ensure precision, though this is manageable given the problem's constraints. Another efficient approach worth considering is binary search. This method leverages the fact that the sum of the first k rows is a monotonic function of k. By performing binary search over the range of possible values for k, we can efficiently find the largest k such that k plus 1/2 equals n. The algorithm works by initializing low to 0 and high to n, then repeatedly narrowing the search space based on the midpoint value. If the sum for mid-rows is less than or equal to n, we move the lower bound up, otherwise, we move the upper bound down. At the end of the search, the upper bound represents the largest valid k. The binary search approach offers a time complexity of O log n, as the search space is halved with each iteration, making it highly efficient for large inputs. Its space complexity remains O1, as no additional memory is used apart from a few variables for the search. The advantage of this method is that it avoids the floating point computations required in the mathematical approach, which can be helpful in scenarios where precision is critical. However, it is slightly more complex to implement compared to the mathematical formula, as it requires additional logic to manage the binary search process. Despite this, binary search remains a strong contender for solving the problem efficiently when simplicity is less of a priority. For this problem, we chose the mathematical approach as the optimal solution. Its simplicity and constant time complexity make it the most efficient and elegant option. By directly using the quadratic formula, we can calculate the result without any iterative steps, which ensures fast performance even for very large values of n. While the binary search approach is also efficient with a logarithmic time complexity, it involves more implementation steps, making it less straightforward than the formula-based solution. As for the brute force approach, it is easy to understand but becomes impractical for larger inputs due to its linear time complexity. The key insight that led to the mathematical solution was recognizing that the problem boils down to finding the largest k such that k plus 1/2 equals n. Solving this inequality using the quadratic formula not only simplifies the process but also ensures the best possible efficiency. While the mathematical approach may be less intuitive for beginners, it strikes the right balance between performance and simplicity, making it the best choice for this problem. The problem is to determine how many full rows of a staircase can be formed using a given number of coins, n. Each row in the staircase requires an increasing number of coins. For instance, the first row requires 1 coin, the second row requires 2 coins, the third row requires 3 coins, and so on. If n equals 8, we can construct 3 full rows, the first row with 1 coin, the second with 2 coins, and the third with 3 coins, totaling 6 coins. This leaves 2 coins, which are insufficient to complete the fourth row. Thus, the answer is 3 full rows. The goal is to determine this number of full rows efficiently for any value of n. To solve this problem, we can start with a brute force approach that directly simulates the process of building the staircase row by row. First, we initialize the total number of coins, n, and set row equals 0 to track the number of fully completed rows. Then, for each row I, we check if there are enough coins remaining to complete the row. Completing the ith row requires exactly I coins. If there are enough coins, we subtract I from n and increment the row counter. This process continues until the remaining coins are insufficient to complete the next row. At that point, we stop and return the value of row, which represents the total number of full rows that can be formed. Let's go through an example with n equals 8 to see how the brute force approach works. Initially, we have n equals 8 coins and row equals 0. For row 1, we need 1 coin, which we subtract from n, leaving n equals 7, and we increment row to 1. For row 2, we need 2 coins. Subtracting 2 from n gives n equals 5, and row increases to 2. For row 3, we need 3 coins. Subtracting 3 leaves n equals 2, and row becomes 3. For row 4, we would need 4 coins, but we only have 2 remaining, so we stop here. The result is row equals 3, meaning 3 full rows can be formed. This brute force approach is straightforward and simulates the staircase building process directly. However, it becomes less efficient for larger values of n. For example, if n equals 10⁻⁶, we would need to iterate through approximately 14 rows because the sum of the first k integers is proportional to k⁻². The time complexity of this approach is O(k), where k is the number of completed rows. Since the sum of the first k integers is k*, k plus 1/2 less than or equal to n, the value of k grows approximately as the square root of n. Therefore, the time complexity can be expressed as O(sqrt, n). In terms of data structures, this approach uses only 2 variables, n to track the remaining coins and row to count the completed rows, making it memory efficient. To improve efficiency, we can use the formula for the sum of the first k integers, s equals k*, k plus 1/2. The goal is to find the largest integer k such that k*, k plus 1/2 less than or equal to n. Rearranging this inequality gives a quadratic equation, k⁻² plus k, 2n equals 0. We can solve this equation using the quadratic formula, k equals -1 plus sqrt, 1 plus 8n/2. The result is the largest integer k that satisfies the inequality. By taking the floor of the solution, we determine the total number of full rows directly without iterating. This optimized approach has a time complexity of O(1), because it involves only a few arithmetic operations and a square root calculation, making it significantly faster than the brute force method for large n. When implementing this solution, it's important to consider edge cases. For small values of n, such as n equals 0 or n equals 1, the result is straightforward: no rows can be completed with 0 coins, and only 1 row can be completed with 1 coin. For large values of n, the algorithm scales efficiently due to its O(sqrt, n, or O(1) complexity, depending on the chosen approach. Another edge case occurs when n is a triangular number, such as 6, 10, or 15. In these cases, the staircase can be completed perfectly, leaving no remaining coins. Lastly, for values of n just short of a triangular number, the algorithm correctly identifies the largest completed row, ensuring accurate results. These considerations ensure the solution is robust and handles all scenarios effectively. This Python implementation solves the arranging coins problem using a binary search approach. The problem requires determining the maximum number of full staircase rows that can be formed within coins, where each row I contains exactly I coins. The function arrangeCoins takes an integer n as input. Instead of using a brute force approach, which involves iterating through all possible row counts, we use binary search to optimize the process. Here's how the solution works step by step. 1. We initialize 2 pointers, left and right, representing the range of possible row counts. Left starts at 0, and right starts at n, because at most, all coins could form a single row. 2. We enter a while loop that continues as long as left is less than or equal to right. 3. At each step, we calculate the midpoint mid of the current range. This mid represents the candidate number of rows we are evaluating. 4. Using the formula for the sum of the first mid integers, mid asterisk, mid plus 1, //2, we calculate the total number of coins required to form mid rows. This is stored in the variable total. 5. We compare total with n. If total equals n, it means we can exactly form mid rows, so we return mid as the result. If total is less than n, it means we can form more rows, so we adjust left to mid plus 1 to search the upper half. If total is greater than n, it means mid rows require too many coins, so we adjust right to mid 1 to search the lower half. 6. When the loop ends, right will point to the largest valid number of full rows that can be formed within coins. We return right as the result. This approach is efficient, with a time complexity of O log n, since the binary search reduces the search space by half in each iteration. It effectively handles large values of n and avoids the inefficiency of a linear or brute force approach. This is the Java implementation of LeetCode problem number 441, arranging coins. The logic mirrors the provided Python solution, using a binary search approach to determine the maximum number of complete rows that can be formed given n coins. Key differences include handling potential overflow with Java's long type during intermediate calculations and explicit typecasting for the return value. The code is optimized for efficiency, operating in O log n time complexity. In this problem, the task is to calculate the maximum number of complete rows of coins that can be formed using a given number of coins, n. Each row requires exactly k coins, where k is the row number. For example, if you have 5 coins, the rows would be filled as 1 coin in the first row, 2 coins in the second row, and only 2 coins left for the third row. This means you can form only 2 complete rows. To solve this efficiently, we use a binary search approach. Let's look at an example where n equals 5. Initially, we set left to 0 and right to 5. In the first iteration, we calculate the midpoint, mid, as left plus right, //2, which gives us 2. Using the formula for the sum of the first mid natural numbers, mid asterisk, mid plus 1, //2, we compute the total as 3. Since this total is less than 5, it means we can potentially form more rows, so we adjust left to mid plus 1, which is now 3. In the second iteration, we again calculate the midpoint, mid, as left plus right, //2, which now evaluates to 4. Using the same formula, the total becomes 10. This total is greater than 5, indicating that 4 rows require more coins than we have available. As a result, we narrow our search by updating right to mid 1, which becomes 3. In the third iteration, mid is recalculated as left plus right, //2, resulting in 3. The total for 3 rows is 6, which is still greater than 5, so we again decrease right to mid 1, now setting it to 2. At this point, the binary search concludes, and the value of right, which is 2, represents the maximum number of complete rows that can be formed when n equals 5. Now, let's consider another example with n equals 8. Initially, left is set to 0 and right to 8. In the first iteration, we calculate mid as left plus right, //2, which gives 4. Using the formula for the sum of the first mid natural numbers, the total is 10. Since this total exceeds 8, we adjust right to mid 1, which becomes 3. In the second iteration, mid is recalculated as left plus right, //2, resulting in 1. The total for one row is 1, which is less than 8, so we update left to mid plus 1, making it 2. In the third iteration, mid becomes left plus right, //2, which evaluates to 2. The total is now 3, which is still less than 8, so we adjust left to mid plus 1, setting it to 3. In the fourth iteration, mid is calculated again as left plus right, //2, which gives 3. The total for 3 rows is 6, which is still less than 8. Since more rows might be possible, we update left to mid plus 1, making it 4. At this point, the search concludes, and the value of right, which is 3, represents the maximum number of complete rows that can be formed. Now, let's quickly look at another example where n equals 1. Initially, left is set to 0 and right to 1. In the first iteration, mid is calculated as left plus right, //2, which gives 0. The total for 0 rows is 0, which is less than 1, so we update left to mid plus 1, making it 1. In the second iteration, mid is recalculated as left plus right, //2, which gives 1. The total for one row is exactly 1, which matches the given value of n. At this point, we can directly return mid, which is 1. This represents the maximum number of complete rows that can be formed when n equals 1. To summarize, the binary search approach efficiently narrows down the maximum possible number of rows by repeatedly adjusting the left and right pointers based on the total coins required. The formula k plus 1/2 helps us quickly calculate the number of coins needed for k rows, and the algorithm ensures we achieve the result in logarithmic time complexity. The time complexity of this algorithm is O log n, and this is because we use a binary search approach to find the largest integer k such that the sum of the first k natural numbers is less than or equal to the given input n. Let's break this down further. First, binary search works by dividing the search space in half during each iteration. Starting with a range of 0, n, the algorithm keeps narrowing this range until it converges on a single value. This halving process results in a logarithmic number of iterations, or O, log n. Within each iteration, we calculate the sum of the first mid-natural numbers using the formula mid**, mid plus 1, // 2. Since this calculation involves only constant time arithmetic operations, it has a time complexity of O1. Additionally, the comparisons and adjustments to the left and right pointers, which guide the binary search, are also O1. When we combine the O, log n, iterations with the O1 operations within each iteration, the overall time complexity of the algorithm becomes O, log n. Let's now consider the best, average, and worst cases for the binary search approach. In the best case, the target n matches the sum of natural numbers at the first calculated midpoint. However, even in this scenario, the logarithmic nature of binary search means the time complexity remains O, log n. On average, the algorithm will perform approximately log n iterations, which also results in O, log n. In the worst case, the binary search must exhaust the entire logarithmic range of iterations, making it O, log n, as well. Now, for space complexity, the algorithm is very efficient. It uses O1 space because it requires only a fixed number of scalar variables, such as left, right, mid, and total, regardless of the size of the input n. Unlike recursive approaches, there is no extra memory used for a call stack, and since the algorithm avoids additional data structures like arrays, it doesn't allocate memory that scales with n. Therefore, the space complexity is conclusively O1. If we compare this to a brute force or naive approach, we can see why binary search is so much faster. In the naive method, we repeatedly sum natural numbers until the cumulative sum exceeds n. For example, in the given code snippet, we increment k and subtract the current value of k from n in each iteration. While this approach does work, its time complexity is O, sqrt, n. This is because the sum of the first k natural numbers grows quadratically, meaning k plus 1/2 equals n, which implies that k is proportional to the square root of n. As a result, the number of iterations required is approximately sqrt, n. Comparing the two, the binary search approach with O, log n, is significantly faster than the brute force approach with O, sqrt, n, especially as the input size n becomes large. Even though binary search and the brute force approach differ significantly in time complexity, they share the same space complexity of O1. Neither method requires additional memory beyond a fixed set of variables, which makes both implementations memory efficient. To further understand why the binary search approach is so fast, we can look at the mathematical justification for its time complexity. In binary search, we repeatedly divide the search range, 0, n, in half. The number of times this range can be halved until it reduces to a single element is approximately log base 2 of n. This gives us the log n iterations. Since each iteration involves only constant time operations like arithmetic calculations and comparisons, the overall time complexity remains O, log n. This combination of logarithmic iterations and constant time operations makes the binary search method both optimal and scalable for this problem. When solving the arranging coins problem, there are a few common mistakes to watch out for. First, off-by-one errors in row calculation are a frequent issue. This typically happens during the transition between the last complete row and the remaining coins. Missteps here can lead to overshooting or undershooting the correct result, especially for small edge cases like n equals 1 or 2. Next, relying on a brute force approach for large values of n, such as 10 to the power of 9, is another pitfall. This method involves iterating row by row, which can result in a time complexity of O, n. For large inputs, this becomes highly inefficient. Additionally, many solutions fail due to poor handling of edge cases. For example, special inputs like n equals 0, n equals 1, or very large values of n need careful consideration to avoid runtime errors or unexpected outputs. Lastly, incorrect assumptions about mathematical patterns can complicate solutions unnecessarily. Instead of leveraging triangular number formulas or other mathematical insights, some approaches default to iteration, which can waste time and effort. Another common error involves floating point precision issues, particularly when using binary search with large numbers. If midpoints or floating point arithmetic aren't handled carefully, the algorithm may fail to converge to the correct answer. This is especially true in languages like Python, where float precision can be limited. On the interview side, there are several key insights to consider. First, this problem has a strong mathematical foundation, as it revolves around triangular numbers. This makes it a great opportunity to showcase optimization techniques like binary search or solving equations. It's also important to understand the trade-offs between different approaches. For instance, you should be able to explain why brute force is inefficient for large inputs and how using binary search or mathematical formulas improves performance. Don't forget that edge case testing is critical. Always ask clarifying questions about inputs like n equals 0 or very large n to ensure your solution handles them correctly. Finally, communication is essential. Clearly articulate your thought process and justify your choices, such as selecting binary search over iteration or formulas. The arranging coins problem shares similarities with a few related problems on LeetCode. For example, LeetCode 367 valid perfect square also involves using binary search or mathematical reasoning to solve. Another closely related problem is LeetCode 69 sqrtx, where the goal is to find the integer square root using a binary search approach. Additionally, LeetCode 744, find smallest letter greater than target, is another binary search problem, but this time the focus is on range constraints. Beyond related problems, it's worth exploring alternative approaches and their trade-offs. The brute force approach is one option, with a time complexity of O(n). While it's simple and straightforward to implement, it becomes impractical as n grows larger. This method works well for small values of n but falls short in terms of efficiency. On the other hand, using a mathematical formula, such as solving a quadratic equation derived from the triangular number sequence, is highly efficient with a time complexity of O(1). This approach is ideal for scenarios that emphasize mathematical rigor but does require a solid understanding of the underlying formulas. The binary search approach offers an excellent balance between performance and complexity, making it the best choice for large inputs where efficiency is crucial. With a time complexity of O log n, it iteratively narrows down the range of possible row numbers until the solution is found. While slightly more complex to implement than brute force, it avoids the inefficiencies of iterating through all rows. This approach is particularly valuable in interviews, as it demonstrates your ability to optimize performance while maintaining clarity in your implementation. By combining mathematical insights with algorithmic efficiency, binary search strikes an effective balance for solving the arranging coins problem in a scalable way. Great job following through to the end. In this session, we solved the problem arranging coins by breaking it down into clear steps and exploring its mathematical underpinnings. Remember the importance of analyzing both time and space complexity and honing your problem-solving skills. Thank you for watching, and I hope to see you in the next tutorial. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!